the last talk of the day. It's a pleasure for me to introduce Professor Alina Bucur from UC San Diego. And she's going to talk to us today about the distribution of point on cyclic L-covers of P1 over finite fields.
Okay, hello everybody, that's scary. So let's see. First of all, I want to thank the organizers for inviting me. It's my first time not only in Rio, but in South America. So more exotic places, please, for number theory conferences. That's good. Let's see. The other thing that I wanted to say before I forget, this is all work that started at an AIM workshop a year and a half ago. So thank you, AIM. And it's, you know how AIM works, so it's going to have a lot of collaborators. So Chantal David, Brooke Fagan, joint work with Chantal David, Brooke Fagan, Nathan Kaplan, and that's like half the list. Mathilde Lalin, Ekin Osman, and Melanie Matchett-Wood. Okay, that's the complete list. So, some of you have heard me talk about this stuff before, so you might know the introduction. There will be a quiz later. And I am going to take advantage of the fact that Kiran and Brian have introduced all sorts of things that I will need for this talk. So let's see. What is the... Let's say that I have a curve, and it's defined over a finite field with Q elements. There are all sorts of questions that one can ask, and one of the questions that has been alluded a bunch of times is, what can we say about the number of points on this curve? And as Brian mentioned, the question becomes interesting, becomes interesting in a different way maybe, when you start thinking not just about a single curve, but about a family of curves. So that's when all sorts of connections with other mathematics appear. So let me sort of remind you a little bit about something that he mentioned, which was the question of that was addressed by Katz and Sarnak, and that's what happens when you look at C is a random curve of genus G, defined over FQ. And what Katz and Sarnak did, they looked at this question for random curves of genus G, and they let the number of elements in this definition field go to infinity. So that's when they can invoke the distribution theory of Deligne and so on and get their results. And if you sort of translate between what Kiran mentioned about the connection between the zeta function of the curve and the number of points in the curve in the definition, one particular case of their work and what they showed was that if you do this in the limit as Q goes to infinity, then, and you vary C, then this, the number of points of C over FQ becomes distributed like the traces of some random matrix in a given ensemble. So it depends a little bit on the family, because maybe I don't want to take the whole genus G family. If you take the whole genus G family, what you get here is traces of random matrices in USP to G. But if you if you want to take smaller families, you're gonna get a different ensemble here. So that's sort of the Katz-Sarnak picture that Brian was mentioning, and he actually mentioned the fact that the zeros of the Riemann zeta were distributed like the like eigenvalues of these random matrices, but if you translate it in terms of number of points, you get traces on the side of the random matrices. So for over finite fields, this is a theorem. On the function field side, over the number field side, well, is you got the picture from Brian, so I'm not going to go back there. So now I'm going to change completely the point of view and go in somehow the orthogonal direction to this and ask how is this number of points of C over FQ distributed as the genus goes to infinity, and this is FQ is going to be fixed. So I'm going to do the opposite of what Katz and Sarnak did. They fix the genus. They let the Q go to infinity. I'm doing exactly the opposite. I'm fixing the Q and letting the genus go to infinity, and that's my family. OK, so this is the question that I'm going to talk a bit about. The story starts with a paper from 2008 by Kullberg and Rudnick. And they looked at the hyperelliptic ensemble. Well, they called it ensemble, I call it ensemble. So what that means is, essentially, they looked at curves with affine models given by an equation y squared is equal to f of x, where f was square free. And they let the degree of f go to infinity, which makes the genus of the curve go to infinity as well. So what they discovered in that work was that somehow what happens here is very much described by actual probability theory. So what they showed is that if you look at this distribution of points, so if you want, this is the probability that the number of points here is Q plus 1 plus, I think they called it S, is the same as the probability that, well, asymptotically the same as the genus grows, the probability that a sum of Q plus 1 independently identically distributed variable add up to S. So by probability here, maybe I should explain what I mean. Since I'm over a finite field, the number of polynomials f of a given degree is finite. So the set of such hyperelliptic curves is finite, and then you just take the naive probability, the number of curves such that with the property that the number of points over FQ is exactly Q plus 1 plus S divided by the total number of curves. That's probability in its. Sorry? I am counting curves with this property. Probability, so maybe this is not going to be so good for, so when I say something like this is equal to something, what I mean is the number of f's with the probability, with degree of f is equal to d, such that the number of points on the CF, I'm going to call this CF here, is over F cube is equal to whatever I had here. Let's put it an alpha, so I don't have to write, divided by the number of F's, degree F is equal to D. And remember, this F were square free, so I'm going to have this condition here and here. That's what I mean by probability. Okay? Wonderful. So this is as you let the degree of F go to infinity. So this, I didn't give you what the random variables are just yet, because I want to give you the formula in general. But the thing that I want to point out now is that this picture seems to hold. Whenever you take this point of view of fixing somehow, fixing the field and taking some family over genus in some way that goes to infinity, or some parameter like the degree or something like this, what you get is the model that you get is this probabilistic model with sums of random variables. And in a way, this is natural, because if you think about it, and I'm going to draw the picture for this, what you look at your curve y squared is equal to f of x, and here are sort of x's. They are on a line. They can take values. Remember, we are over fq, so in a way, this is my p1 fq. And this curve is going to be like a twofold cover of this guy. So what's going to happen is that you're going to have some points here for which f of x happens to be a square and a non-zero square, and then you get two solutions for y. So you get 2 points on the curve upstairs. You can have f of x is equal to 0, in which case you have only one double point, y, that gives you y equals 0. And then it can happen that f of x is not a square over fq, so you do not get any points over fq, right? So those are essentially the two things that can happen, and that tells you exactly where my random variables come from. They come I have one variable for each point of that p1 guy over fq. So in a way, the situation is, intuitively, it's relatively clear what is happening here. So what the subject for today is a generalization of this point of view, which is what we call L-cyclic covers. So I'm going to sort of switch to geometry. So what do I want here? I want, again, I have my cover of P1, and it's a degree L cover, but it's not just a degree L cover, it's a cyclic degree L cover, which means, if you want in terms of geometry, it means that if I look at the automorphism of C over P1, this guy is isomorphic to Z mod LZ. So L-cyclic here. OK. So if you want the equivalent of some affine model like this, could be y to dl is equal to f of x. And you just look at that. OK. So what the sort of picture that you have here, again, you have the same point of view in a way. You have the points on P1, and now you just have something with more sheets here, L sheets, and you're just counting the probability that you just figure out, OK, how many points can I possibly have over a point of P1? because I'm actually, yes, that is a very good point. So I am going to assume that Q is congruent to 1 mod L, which is an important assumption because, as I suppose Felipe was worried about, the point is that if I have that, then I have L distinct L fruits of unity in there. So I actually have L solutions for y to the L is equal to f of x. If I have a non-zero solution, then I have L of it. OK? That's an important restriction. Yes, I am totally assuming that. OK. So you have these L cyclic guys. So let's see what we can, if we can reproduce this point of view. So what can happen for each point over P of P1 on the fiber? What can happen in the fiber above a point? Well, since you have this L cyclic business, you have only 3 possibilities. That are essentially the possibilities from here. So maybe I should put, if I have an x here, and this is my cover pi, what can happen to pi minus 1 of x? It can have only either no point, or 1 point, or L points, nothing in between. That comes from the fact that I actually have a Galois cover, so I don't have any intermediate behavior. And now, somehow, the game becomes try to figure out what's the probability that a fiber has 0 points, a fiber has 1 point, or a fiber has L points. That's what you get. OK, so in other words, what you have to do here is figure out you can figure out what happens at the level of the function fields of these 2 curves. So right, whenever I have a curve over FQ, I can just take the field of functions or regular functions on that curve. And what I get is a Galois extension of fields here. So maybe I should put that down. I will sort of this. So whenever you have this cover, you take function fields here. So, and you get an extension L over K with the property that, so remember I have this automorphism. Sorry, this is a normal C, P1. So one such, all this data, a cover map, an L degree cover map with an isomorphism to Z mod LZ, what gives me here is an extension of degree L together with an isomorphism of the Galois group of the extension to Z mod LZ. So that's isomorphism is determined already. Yeah. I need that. This 0, 1 L business does not hold true unless I. Sorry? Yes, but when I actually want to compute later on, I will actually need that condition because I'm going to sum over the. So far, in principle, you can write this problem and then you can just use Kummer theory and do something similar to what I'm about to do, but I don't want to go there in this talk. OK, so let's continue our story here. What does it mean for a fiber to have 0, 1, or L points? It corresponds, if you want to think about this, a point here corresponds to a place, and the degree 1 place at that of k. And you want to know, you're going to have 0 points when V is inert, 1 point when V ramifies, and L points when V is split. And because I have a Galois cover, those are the only possibilities. I'm not going to have any sort of funny behavior. So I'm going to have this 0, 1, L. This is when V is inert. This is when V ramifies. And this is when V is split. Splits completely. So I cannot have any behavior in between that. OK. Now, I will leave that on. There. So if you try to look at what Kullberg and Rudnick did, what they did was write the number of points in FQ as Q plus 1 plus a certain character sum as chi of F, number of points in, let's CF for, remember, CF is this. Y squared is F of X. And this S chi of F is just a sum of chi of F of X over all X in P1 of FQ. And chi is just is the quadratic character, the quadratic residue character. On FQ. Right, so chi of alpha in FQ is going to be 1 if alpha is a square, 0 if alpha is 0, and minus 1 if alpha is not a square. That's just the most simple-minded character ever. OK. So, and then they try to look at this. They actually prove that they actually take the probabilities that alpha and compute the probability that a polynomial f of x takes value 0, takes value a square, takes value a non-square, and they put it together. So you can try to do this for cyclic cover. So this was for hyperelliptic. For L cyclic, you can try to do the same thing. You're just going to get more characters. So if I look at y to the L is f of x, and I call this my CF, then the number of points here is going to be q plus 1 plus, now I'm going to have L minus 1 character sums, and they look very much like that, except that this is supposed to be a chi, and this is an x. Now they look like this, and these chi i's are just the L minus 1 characters of order L. Non-trivial characters of order L on FQ. So very similar to this guy. Now, when you try to do this, you run into a little bit of a problem trying to let things go to infinity, because you impose your conditions. So what is the, for these covers, I want it, for the hyperelliptics, I wanted F to be square free. The thing to impose here is that F is L power free. So that means that you essentially take your F and you write it as a bunch of a product of F1, F2 square, FL minus 1 to the L minus 1, where Fi's are all square free, and they are relatively prime, so you don't accidentally get any L powers in there. And then it turns out that if you want to try to do something like this and compute the distributions, you need the degree of Fi to all go to infinity, not just one of them. And that is a little bit of a problem because the genus of the curve is really something related to the sum of the degrees. So you're not really looking at the whole genus anymore. You need this sort of condition. But with this condition, this is a subset of those people, namely myself, Chantal, David, Brooke Fagan, and Mathilde Lalenne. We managed to do this using this point of view, and we showed that the probability that a curve is Q plus 1 plus S. Actually, maybe I'll write it like this. M points is the same as probability of a sum of random variables is equal to M. Is modeled by that. And the xi's, let's write big xi's over here. Zero, 1, L, my variables. And nothing goes wrong with the statement. I need it for the proof because when you try to prove things like that, you prove main term plus error term. And it turns out that in the error term, you really get q to the minus d1 plus something in terms of q to the minus d2 and so on. And you want that thing to go to 0, and the only way to convince it to do so is to let all the degrees go to infinity. So, yeah. That is, so essentially, thank you for the lead, Jordan, because the whole point of this project was to somehow remove that obstruction and see what happens when you remove it and get the probability for the whole genus. OK, so yes, this is, that is a subset. And we are not going to say what the subset means. So. OK, so let's see what my probabilities were. Here somewhere. You'd think that I know this by heart, but I don't. There we go. So ramified, that's 1 over L1 plus L minus 1 Q inverse. 0, that's the inert guy. So this is L minus 1 over L1 plus L minus 1 Q inverse. And the last one, which is the split case, 1 over L, 1 plus L minus 1, Q minus 1. Do I have something wrong in here? Sorry? Yes, the ramified one fails to have this L, sorry. And now they have the great property that they actually add up to 1. OK, so those are my 3 probabilities. And maybe, so what we were interested in doing was partly removing this constraint about the fact that I needed the degrees of all these guys to go to infinity. And the other the other thing that we wanted was to sort of figure out what happens in reality, because somehow, since we are imposing this condition for all the degrees to go to infinity, it means that I'm not looking at the whole moduli space of cyclic L covers of a given genus and let the genus go to infinity. I'm looking just at certain connected components of that moduli space that are indexed exactly by, it turns out that the moduli space has these components indexed exactly by these degrees. But somehow you should be able to cycle through the degrees and so on. So I'm not going to go into the connected components of a moduli space, because I know at least one person who would run screaming, namely my advisor. OK. OK, so let's see. The other thing is, OK, so I have this part of the moduli space. And for L equal 3, there were at least 2 competing results. So if you look at this result, what you get is these probabilities, 0, 1, and 3 points, with probabilities here is 2/3, 1 plus 2 Q inverse. 1 is 1 over 1 plus 2 Q inverse. And here I have 1/3, 1 plus 2 Q inverse. And now I realize that I have a Q inverse missing from the ramified guy. So this actually had L minus 1 Q inverse. I have my probabilities all wrong here. Yes, this is L minus 1 like this. So here I actually have the 2Q minus 1, which makes it work. OK. So these were my probabilities. And then there is this competing work of Melanie Woods with 2 of her students. So it was the work of Cheung, Wood, and Zaman. And they had slightly different probabilities. They had 0, 1, and 3. So they were indexing things a little bit differently. And what they had gotten was 0 with probability 2/3 times 1 plus Q inverse plus Q to the minus 2, 1 with the probability Q minus 1 plus Q to the minus 2 divided by 1 plus Q inverse plus Q to the minus 2, and then the other one is 1/3. Like that. So for L equal 3, at least, you had 2 competing results. Here, they were indexing slightly differently. Namely, they were letting the degree of the whole F go to infinity. So the question was, in addition to removing this degree of F I have to go all to infinity, is to figure out what is the real story for the moduli space. And this is pretty much how things were when we all met at AIM in January last year. We had these 2 competing results, and we were trying to sort of figure out what happens and what the reality is. So somehow it was clear that you cannot really adapt this generalization of Kullberg and Rudnick with character sums to get to the whole space, because you need these technical conditions for your error terms. So that was a no-go from the beginning. But starting with this, you still have this powerful machinery, because now you have your over finite fields, you have this corresponding Galois extensions, and you have more than that. You have all sorts of other interesting things. So let's see. I still have my thing there. And what's the idea? The idea is to use first of all, Galois theory. Galois theory tells me that, right, L over K such that together with an isomorphism like this, so this equivalence classes of such Galois extension are actually in one-to-one correspondence with maps from the absolute Galois group of K to Z mod LZ that have the property that are continuous, continuous surjective homomorphisms. GK is the absolute Galois group of K. Okay? And then, so that's Galois theory. And then by class field theory, maybe I'll put it here, this is in one-to-one correspondence with maps from the ideal class group to Z mod LZ, again, continuous surjective homomorphisms. Here too. So the idea is to get this point of view, employ this point of view, and sort of translate everything in terms of maps. So the first thing that you want to translate is the genus of your cover. And it turns out that what you get when you do that translation is that the genus of the cover is actually L minus 1 times minus 2 plus degree of the conductor of, let's call this map something, phi. Conductor of this map, phi. And conductor means pretty much what you think it means. It means it doesn't ramify is the places where it actually ramifies. OK. And I'm supposed to close my bracket. So somehow, there is this very simple relation between genus of the cover and the degree of the conductor of this map over here. And letting the genus go to infinity is the same thing as letting this conductor go to infinity. So this comes from, well, the usual things, Riemann-Roch and the relation between discriminant and conductor and things like this. So maybe, and you can, so the conductor is really the sum over V ramified of degree of V. So you have something like this. And now you can sort of bring this machinery of maps to bear on your problem. And let's see. How much do I want to say about this? Because it's already, so maybe I should finish in like the next 5 minutes or so I don't overlap with drinking time, which I learned is a very bad thing.
Start drinking while you talk.
Hey, that would be very unfair to me. I don't think info would approve, eh? OK, so how you deal with this sort of thing is something that will make maybe the analytic number theorists happy, because you actually have, before I make them happy, you have to make one more translation. So a map phi like this, you actually have to think of it a little bit differently. I'm going to think of it in terms of some maps. Well, let's call them psi. Very much a Delic notation here. Disclaimer. To Z mod LZ, that's trivial on FQ star. So you have these maps. This guy is a uniformizer at infinity, so somehow I'm pushing everything to infinity, and this is just the abelian group generated by that. And then I have this units in the local rings at each place. Remember, this has something to do with dells, so it's natural that I get something like that. So somehow I'm going to choose the place at infinity to explore the deeper structure. And for such a map, so maybe I should say V ramifies in L over K is equivalent to saying that if I take the component over V here, phi V, which is this guy, is non-trivial. So it's a very, at least for the primes that ramify in my extension, the condition is very simple. For split and inert, the condition is a little bit more complicated, and then there is a certain compatibility condition on in order to take into account the fact that if psi is supposed to be trivial on FQ star, but I'm not going to get into that right now. Okay, so what you do is the method is to actually, once you have this whole picture, is to go back to tried and true analytic methods and proceed very much along the lines from a paper of Wright from the 80s, if I remember correctly. And that is to make the generating function f of s sum over extensions L of k that have Galois group Z mod LZ of 1 over absolute norm of discriminant L over k to the s. So that's your Dirichlet series right there. And then employ classical analytic number theory techniques, namely the Tauberian theorem and so on, to count how many extensions of a given norm of discriminant do I have, which really amounts to how many extensions of a given degree of discriminant I have, which is exactly what we want. It means a given genus for my curve, given that relation between the degree of the conductor. Oh, maybe I should put this in terms of the conductor. It turns out that in this situation, the norm of the conductor is, the norm of the discriminant is just norm of the conductor to the L minus first power. So you just use this and use analytic number theory to figure out how many you have. And the upshot in the end is that you get exactly these probabilities that I have here. So somehow this picture actually extends to the whole moduli space. So maybe I will end there. Perfect on time.